Hi, Dr. G here. I'm going to try to walk you through a homework problem that I did not explain correctly on Wednesday in class. So this is assignment 7.2. This was on diagonalization, and this was problem number 12. In this problem, they give you two 3x3 matrices. They're both diagonal, and they ask, are the two matrices similar? I think that part was fairly easy for most people. Because they're diagonal, we know that the entries along the diagonal are the eigenvalues, and so we can see that these two matrices have the same eigenvalues, and we have a theorem that says that two matrices are similar if they have the same eigenvalues. So that part was okay. It was the second part that became a little bit problematic. The second part says if they are similar, find a matrix P such that the matrix B is equal to P inverse times A times P. So we know from the proof of theorem 7.5 that if the matrix A has three linearly independent eigenvectors, then we can get the matrix P by lining up the linearly independent eigenvectors as the columns. And P is invertible because the columns are linearly independent. And then when we multiply matrix A on the left by P inverse and on the right by P, we're going to get a diagonal matrix B. Now the key to that proof of that theorem is that the order in which we put the eigenvectors of A in as columns of P, that determines the order of the eigenvalues in B, the resulting matrix B. So let's give the eigenvalues of A some names so we know what we're talking about. So let's say lambda 1 is 3, lambda 2 is 1, and lambda 3 is 2. Now look at the matrix B. The first eigenvalue that appears there is actually lambda 3. The second one is lambda 2, and the last one is lambda 1. So that's the order that we want to put the eigenvectors in, the corresponding eigenvectors. So the matrix P is going to be, the first column is going to be P3, the second column is going to be P2, and the third column is going to be P1. So let's find them. P3. And we're going to find P3 by finding the null space of lambda 3 times I minus A. Lambda 3 was 2, so 2I minus A is this matrix. And we can tell by looking at it that the null space is spanned by the vector P3, which is 0, 0, 1. Okay, let's do the same thing for P2. P2 is going to be a basis for the null space of lambda 2 times I minus A. Lambda 2 was 1. So 1 times I minus A is this matrix. And we can tell by looking at that it is spanned by the vector P2, which is 0, 1, 0. Right? And the final one is P1, which is going to be lambda 1 I minus A, the null space of lambda 1 I minus A. Lambda 1 was 3, so 3I minus A is this matrix. And P1 is then 1, 0, 0. Great. So that means that P is going to be P3, P2, P1 all lined up. And we see that P is an elementary matrix. Remember what an elementary matrix is. An elementary matrix is a matrix that is the result of a single elementary row operation performed on the identity matrix. So we can see that this one is the result of swapping row 1 and row 3 on the identity matrix. So what's the inverse of that? It's the same matrix. the inverse of swapping those two rows is swapping them again. So P inverse is the same as P. Okay, so now let's do the multiplication and make sure we got the right matrix. So P inverse AP is, here's P inverse, there's A, here's the matrix P, same as P inverse. Okay, I'm going to multiply P inverse times A. I get this thing. Now I'm going to multiply that on the right by P. And I get this, which is the matrix B, exactly what we wanted to get. So the key was to remember that the order of the eigenvectors, when you line them up in the matrix P, the order is going to be the same as the order of the corresponding eigenvalues in the resulting matrix B. Okay, if you still have questions about this one, don't hesitate to send me an email. In the meantime, have a great weekend. Good night.